Hello, everyone. My name is Brandy, and I'm here today with Nathan Bronson. We are from a company called Rockset. Rockset is building a real-time analytics database. And so these things have at their heart a bunch of very, very interesting problems, one of which is in the title of my talk today. Now, that title might not mean anything to you yet, but my goal in the first half of this talk is to explain basically what problems we're dealing with, like what problems are inherent in the things we're building, and then turn it over to Nathan at the halfway point to explain how we're solving some of those problems. All right, so let's jump into it. So Rockset, I said this, real-time analytics in the cloud. These are, let's be honest, buzzwords, but they do a lot of work. So I want to go through them one by one and explain what these mean and how they constrain what we're building. So first, analytics. So analytics means basically the ability to query the data you already have, ideally in the way you want to query it. The gold standard here, as far as the API goes, is SQL. SQL is the lingua franca of analytics. It's not the only way to do analytical things, but in general, it's the way it's done, and it is the way that Rockset lets you query its data. The data we're ingesting comes from many different places. The traditional, most obvious place it comes from is your traditional OLTP databases. So this is things like the MySQLs of the world, Postgres, things like that. Also, document-oriented database. These are things like Mongo or DynamoDB. But data can even come from other things that aren't necessarily even queryable in any native way. So things like an event stream, say in Kafka, or an S3 bucket, or maybe even a file. And the data in all of these varied things can also come in a wide range of forms. It can be structured data. It can be semi-structured data. It can even ostensibly be unstructured data. Now, one of the core premises of Rockset is there's not really a lot of unstructured data in the world. Most data, almost all data, has some inner structure. And spoiler alert, that will become a main character in the story to come. Second, real-time. So real-time has two really important meanings for us, really two important consequences for what we're talking about today. One is on the input side, one is on the output side. On the output side is the queries. So queries to Rockset need to be fast, and in particular, selective queries. If you want to know about the event that happened between A and B that had a characteristic C, D, and E with users X, Y, and Z, and there's 5 answers, you should get those back really quickly. Quickly here is on the order of milliseconds. I want you to be able to hook this up to a UI and show a user, a human, and have that button click feel good, right? That's what real-time means in this case. Second is the data latency. So I want the data to be fresh. If you give Rockset some data to process, I want it to show up in your queries on the order of seconds. So we can't do a batch update. I can't queue data for an hour and do one massive update every hour. I need updates to be continuous and effectively streaming on the ingest side. So that's real time. And then finally, we have the cloud. So the cloud part is really valuable. There's 2 main benefits that come from having a cloud or cloud-like setup. So the first is you get to disaggregate your system. So I can put the compute-y parts of Rockset on compute-optimized nodes. I can put the storage-y parts of Rockset on storage-optimized nodes. And more importantly, getting to the second one, these are elastic. So I can scale up compute very quickly. I can scale up storage very quickly, or scale down, as the case may be. These benefits are obviously huge if you have elasticity and disaggregation, but we're not going to be talking about them today. So a talk just like this could be given with this exact slide, expanding on this, double-clicking here, but that is not today's talk. You'll have to come to the next talk for that one. So what is my agenda? So going into this whole schemaless ingest and schemaless query, I want to lay out some very obvious problems. So I'm going to drill into this and lay out some very obvious problems with attempting to do this, and then I will turn it over to Nathan to solve all my problems. So 2 key design points in Rockset that get us there, and this is what we'll be talking about a bit later. So this first is this vectorized query engine. So this is a term of art, and basically what it's doing is taming the dynamicism. So you are giving me arbitrary amounts of unstructured, ostensibly, unstructured data, and it's my job to figure out how to leverage that data's inner schema to be fast. That's one thing that we're going to be building. Then the second point, which may be a little more subtle but is very important, is this needs to be done recursively into nested documents. So if your JSON has sub-JSON, as it were, I need to index and make that queryable in exactly the same way the outer document is. So this is what Nathan's going to be digging into in a bit. But before I get there, I want to make this really visceral. Imagine you're building a system. Coming down a pipe is a stream of JSON documents. You want to ingest that in some way to make it queryable. Most naive implementations, and many people have done this, fall into exactly one of two categories. One, naively, you can assume that the data has a fixed structure. You can make SQL tables with that structure. You can parse the JSON and plop it into the tables and set up all the foreign keys correctly and all the indexes properly. And you will get screaming fast queries out the other end of that, assuming all your indexes are set up correctly. The problem is this is one, super labor intensive to set up, and two, it's super hard to change. This isn't bad necessarily, but it's a huge impedance mismatch with what you typically want from analytical workloads. Analytical workflows usually want things to be more ad hoc. They want more fluid. Add a field here, query the field over there. The whole like fixed rigid structure tends to work against what you're going for in an analytical workload. The second thing you could imagine doing is go full dynamicism, right? Just store the JSON as a column in the database. Now it's super easy to dump data in. The schema can change however you want. The only problem is you've tossed out the reason to use a database to begin with. You don't get any indexes. Your queries won't be really fast, and effectively everything will turn into a table scan. Right? So this represents basically the heart of the problem, and at least part of the heart of the problem, and one of the things that we're trying to solve at Rockset. To double click slightly more, to make this even more obvious, at the very, very, very heart of all of this dynamic stuff at Rockset is this type. It's a C++ type, so it's my favorite. It's called iValue. So iValue is a tagged union, right? It is a tag with some data. The tag tells you the type of the data. And then we can build iValues out of iValues. And so you could, for example, have an array of iValues, and an array of iValues is itself an iValue. So these things are giant, nested, recursive, dynamic types that can hold any type that SQL can hold. So this might be familiar to some of you who are familiar with the idea of fully dynamic, for example, which is a very similar data structure, except it supports the types supported by JSON as opposed to SQL. Now, if we just use iValue everywhere naively, you run into immediate problems. And this is where the ideas for solutions begin to emerge. And you'll see that in a minute. Imagine I give you 1,000,000 integers. Well, you store them as 1,000,000 iValues. So you have 1,000,000 iValues in memory or on disk. And every single one of those 1,000,000 has a tag that says, yes, I am an integer, right? That's a pretty big waste of space. And every single piece of code that tries to iterate through 1,000,000 integers will have to check, are you an integer? Yes, I'm an integer. So there'd be a huge amount of compute wasted dealing with all of these dynamic integers. So you can start to guess at how we might want to fix this problem, how we might want to reduce all that waste in terms of storage and compute. But I'm not going to tell you how we do it. I'm going to let Nathan tell you how we do it. All right, Nathan, you're up.
Thanks, Lewis. My name's Nathan. I'm a software engineer at Rockset, and I want to talk about how we're going to take those fine-grained tags and the overheads in our inner loops, and we're going to move them out so that we can amortize them away. So one of the effective and widely used techniques for making a database query engine, even one that has strong schemas ahead of time, for making it faster is called vectorization. So vectorized here doesn't necessarily mean that we're going to use vector instructions, although they often go together. A vectorized query engine is one where we take, instead of operating on individual rows in our engine, we process and communicate in batches of thousands of rows. And the batches are represented not in a row major format, but in a column major. So each column will be an array of the values present just in that column. This is similar to the transpose that you do in high-performance game programming, where you replace an array of structures by a struct that contains arrays. Vectorization was originally designed to amortize the costs of interpreting the query plan, even in a database that has a strict schema up front. But it turns out that vectorized query engines are also really good at exposing and letting us amortize the overheads of having no schema at all and of having dynamically typed data. So our general strategy is going to be to get rid of these arrays of tagged unions, or augment the arrays of tagged unions. We're going to take our iValue tagged union type, and we're going to add a whole bunch of other types of arrays to it. We're going to have an array of integers. We're going to have an array of strings with a dictionary encoding, so it's better. You can have an array of timestamps. Now the tagged union can now select dynamically among many array types based on which one matches the data that we've actually observed. This is going to let us get rid of all the tags on the leaf elements, and it's also going to let us specialize all of our core loops for each of these concrete types, and then do a single dynamic dispatch to the entire loop. So rather than having to do dynamic checks inside our inner hot loops, we're going to be able to hoist the checks out. And we do this by using C++ C++ template expansion. So we generate, like if there's n array representations, we generate either n copies of something, or sometimes we generate n squared copies if we want to generalize over two array input types. Then we build a kind of run-of-the-mill vectorized query engine. And then we use our I-value arrays as the vector form for a particular column. There's a little bit of a chicken and egg problem here, which is in order to do a vectorized query engine, we have to know the columns ahead of time. And if we don't have a schema, where does that come from? So it doesn't actually turn out to be that big of a problem, because by the time we actually are trying to run the query, we know the query text itself. And almost all performant SQL queries mention all the columns that they're returning explicitly. Like people don't really use select star in their production query workloads. So this is what we call schema on read. So we actually extract the columns that we're going to be using directly from the query itself. Once we do this, we can dynamically pick the best representation. And there's actually several points in the lifetime of data where we can do this. The best case, and this is the common case, is that we actually can notice that a particular range of rows, a column in that all has the same type at ingest time. So if we have a block in our index structure, or maybe in one of our other storage formats, we can encode that with a compressed encoding all the way on disk and preserve that compressed encoding all the way back out as we process it. Even if it doesn't come from disk, kind of pre-tagged with a type, we can still heuristically determine that we need to do that later. If we're going to be using an array multiple times later, it's actually worth it to recode it so that then the subsequent uses of that will be faster. So I talked a little bit here about we want to be able to use templates to instantiate our code multiple times. There's multiple ways in which we do that, but one of them, which I really like, is using generic C++ closures. So this is a slightly contrived example. I have to fit the code on the screen, so I can't use a real operator, but this is a function that computes the number of bytes that will be used if we duplicate the last element of an array an additional number of repetitions. So we're given an I value, this is the tagged union type, and it contains an array, but we don't know what kind of array. There's maybe a dozen possible concrete types. So the first step is to call a function array type dispatch. So this is a function that internally it has a case statement that can recognize each of the 12 different concrete array types, and then it will actually call the closure with the concrete type. And we don't know what the type is ahead of time, so we have to use an auto type on our closure. The effect of this is that the closure itself is now as if it's a templated method, and each of the different places that we call it inside array type dispatch with a different argument type will cause a separate instantiation of the body of the closure. So we're going to get 12 different bodies, one for each possible array type that we have. Inside the closure body itself, we actually have a concrete type available. We don't have a name for it yet, so we have to use decal type to find it. But once we do that, then we have access to the name as well, and we can even do things like reading out dependent types. This is generic programming, but sometimes the body actually varies slightly from one to the other. Maybe we want something slightly different if it's a dictionary encoded. Maybe we want something different if the value type can kind of recursively own other things. So in this particular case, if this is an array of I values, it might actually be holding data indirectly. So size_up doesn't actually capture the value. But on the other hand, if this is an array of primitive types, there's no byte size method you can't call int.bytesize because int doesn't have any methods. So what we do is we take advantage of compile time if statements. So what we have here is we have a predicate that can be evaluated at compile time, and we say if const_expr and then the compile time predicate. Inside the branch, that code only needs to compile when the predicate is true, and then the else branch only needs to compile if the predicate is false. So we tend to have this pattern where we can have a generic method, but maybe we collapse our generic code down from 12 possibilities to 2 or 3. And then we get a lot of benefits from this in the long term. So popping back up to a higher level, there's a problem that we kind of glossed over, didn't mention before, which is that the data that we get that doesn't have a schema, if we're getting it from a source that's a document-oriented database or JSON, it also has nested structure. In a relational table, if you have, for example, a set of zip codes that go along with a branch office, you would put that in a separate table and there would be a foreign key relationship and you would join in order to get them together. In a document-oriented model, it would make more sense to just include this array as a nested structure. And so sometimes the documents that we get in actually have a lot of nesting. If we had a static ETL tool, we would flatten these in order to be able to index it, but we don't want to have to do that step. We want to be We want to be able to ingest the data as it comes and without knowing the schemas ahead of time. But we still need to be able to build indexes that let us run this kind of query efficiently. So if we only have access to flat data, the only way we can run array contains is to deserialize the array and scan it, which is not going to be very efficient. What we really need to do is we need to build an index structure that indexes the leaf elements of the nested structure rather than just the top level. So we have the ability to dynamically construct column names, because we didn't know them ahead of time. So a first attempt at this might be to try to use something like a JSON path or a path identifier that tells us exactly how to get to the leaf from the top level document and use that as the column name. So I want to briefly mention a higher level point here, which is that there's actually a very deep symmetry between indexing and sorting. When we have an inverted index, we kind of tend to think of it as something that maps the value to a set of rows that might have that value. But it's actually something that maps the column name and the value to the set of rows that it's in. The column is usually, in the case of a database that has fixed schemas, the column is usually part of the metadata of the index rather than being stored along with every entry in it. But conceptually, it's there. And you can remove it dynamically with prefix encoding. You don't necessarily have to put it in the metadata ahead of time. So if we use dynamically constructed paths as our column prefix, and then we have a sorted structure, we actually get an inverted index that we can use to find anything in the nested document. So for example, if we're looking for a name and we want to look something up by name and the name San Mateo, then we can construct our lookup key in the inverted index, which is name San Mateo, and we'll find what we're looking for. But this doesn't quite get us to being able to use an index lookup for the query that we saw before. And the challenge here is that when we're navigating through a nested structure, it tends to be that when we're navigating into an array, we don't really care. We're trying to quantify over the array index. We don't know what array index we're looking for ahead of time. So the fact that we encoded the array indexes here makes it so this index structure doesn't actually let us do what we want it to before. If we were looking only for documents where the 0th index happened to be the zip code we were looking for, then it would work. But that's not that useful of a query. What we can do, though, is we can take everything that we don't expect to know and we move it from the left side of the index to the right. So in this case, we expect to not know the array indexes that we're looking for, so we'll just replace them with a wildcard, and then we'll store the actual array indexes on the right so that we can recover them later. We don't need it in this particular example, but it's useful in many others. Now we actually have enough information from the query to be able to construct a key to go look into our inverted index. And the result of this is Rockset actually can take this show me all the keys where array contains happens to match this value and turn it into a single point lookup against an inverted index. And we can run this very, very efficiently. So the wonderful thing that's happened here is that it's only a small step from efficiently supporting schemaless flat data to being able to efficiently support schemaless nested data. So we can build inverted indexes, and we can use a similar technique to get the benefits of columnar storage formats also on the nested data. To sum up, Rockset is fast because of a confluence of two happy events. The first is that vectorized query execution, which was originally developed to make relational schema-based databases faster, actually works really well at letting us amortize away all the costs of not having a schema and having dynamic types. And the second is that once we have good support for dynamic types and flexible schemas, it's not a very big step to get from there to being able to also efficiently handle nested data. These things together mean that Rockset can efficiently take nested JSON in and give you fast SQL out. Thanks for listening, and I hope you enjoyed.